Good day, everyone. My name is ROSHINI. I'm doing Bachelor of Computer Science majoring in Bioinformatics, and I'm currently in my fourth year, second semester. Today, I would like to present the video demo for my FYP, which is entitled Classification of Breast Cancer using Deep Learning based on integration of single omics variations data. So first of all, I would like to present about the data pre-processing step for both concatenated data integration and also similarity network fusion. So first of all, I import all the necessary libraries that required for the pre-processing. So here is the library, which is I import NumPy, Pandas, Matplotlib, Seaborn, warnings, everything. So after that, in order to connect with my Google Drive, because I import all the data set in my Google Drive. So first of all, I connect this Google Colab with my Google Drive, and then I create a data part for each of the in order to import each of the data set. So here is the part one represent the clinical data set, part two represent the material data set, part three represent the miRNA data set, and part four represent the SCNV data set. So next, I import three different omics and also one clinical data. So here is the raw data set. So which is I rename as DFO. So DF1, DF2, DF3. So here I import the CSV file using PDRead, and then this is the shape of the each of the data set. After that, next process is the removal of duplication data. And then exploratory data analysis. First of all, I check for the non-null observations and also the total number of entries for each of the data set, the three omics data set, which is methylation, miRNA, and also the SCNV. So, and then I print each of the data set to have a clear view on the data set. So here is the clinical data, methylation, miRNA, SCNV. So next, I check for the missing values that are present in the data set. First of all, I check the missing value in the clinical data. And then for methylation data, here is for the miRNA and also the SCNV data. After that, I check for missing values in form of zeros. So if there are any columns or any attributes that contain the zero values. So here is the result for the clinical. This one is the zero values that are represent in the methylation. And then here is the zero values that present in the miRNA. And here is the zero value that presents in the SCNV. So next, I replace the zeros with nonce. So this is the formula that I use to replace the zeros with the nonce. And then next process is replacing null or none values with standard deviation. So this process is called as imputation. We have a lot of imputation methods, such as we can impute using mean, mode, median. But here I used standard deviation to impute the missing values that in the form of null or also the none values. So this is the okay. So here is the number of nonce before filling, and also here is the number of nonce after the filling. So after I input all the values, I print the data set. So this one is the DNA methylation, and next one is miRNA. So before that, before I go to the miRNA, I check whether, in order to reconfirm, I check whether there is any null values or none values present. So here it shows no null or none values are present. So that means I have successfully imputed the missing values using standard deviation. So next one is for the miRNA data set. I use the same formula, just the data set will be different. So next, same, I print the data set in order to see whether there is the process is successful or not. And then lastly, in order to reconfirm whether there is null value or non-null value. If there is any null value present, it will print null or none values are present in the data frame. If the process is, if I have successfully imputed using the standard deviation, then it will display no null or none values are present in the data frame. Okay, next one is for the NC and SCNV data set. So the same process repeated. Okay, next one is omics data without null values. So here we already have omics data without null values. So and then I print for the info for the methylation, miRNA, and also the SCNV. After that, after I input all the null values, the next one is dropping all columns except sample ID and also type in clinical data. This process is carried out in a clinical data set. So it is carried out in order to change everything into numerical values, the binary classification. So this process we called as a data encoding. So first of all, I print the attribute name. So this one is represent the sample ID and also the POM50, the type of breast cancer. And we have a few types of breast cancer that present. So we can see here we have luminant A, luminant B, basal, and also we have few non values. So first of all, we have to check whether there is a null value present or not. So here it's clear that there is null value present. So when we print, it shows null or none values are present in the data frame. So the next step that we have to do is we have to replace the none values in categorical column of clinical data set. So we replace the none values with the most frequent value in the category of the column. So after we impute the most frequent value in the category, so there will be no null values present. So if you can say there is luminant A, basal, B, and then we, in order to reconfirm whether there is a null values or not, we can use this code. So if there is any null values, it will bring null or none values are present. If not, it will present not present in the data. So here we can identify, we can get to know that there is no null or none values are present. So the data imputing process was successfully carried out. After that, class distribution. So here, first of all, we have to look for the number of the types of breast cancer that present in the data set. So we have luminant A, B, basal, HER2. So after that, we have to convert the multi-class to binary class for my thesis. So I just drop the basal and HER2 since it's the rare cases that found between the patients. So luminant A and luminant B is the most frequent cases that occur between the patients. So I use luminant A and luminant B for the binary classification. And then I drop the both column and filter the column to luminant A and luminant B. After that, replacing class with value. So I replace luminant A and luminant B with binary numbers, luminant A as a 0 and luminant B as 1. So after that is renaming the column heads in order to have a clear understanding for the next process. So attribute name is converted to patient ID. It's repeated for all of the data set. And then POM50 is replaced with class. So after this process, data filtering is carried out. So we extract the common values from the 4 data sets and filter the data based on the common values. So here is the shape. The 3 data sets now contain 167 samples. And then here is the finalized data for clinical data, methylation data, miRNA data, and also the SDNV data. So after we have successfully carried out the pre-processing, I have stored the pre-processed data in a different Excel sheet. So this is the code that we can use to store a new Excel sheet. So after this process, the integration method will be carried out. So as I said, there are 2 types of integration methods that I used for my thesis. The first one is concatenated data integration, which is known as the traditional data integration. And then the second one is SNF, similarity network fusion. So first of all, I would like to explain about the concatenated data integration. So first, I import the pre-processed data set, and then setting patient ID as data index. So patient ID is set as data index for all of the data set. And then here is this is the code that I use to integrate all the three omics with class embedded. So after I integrate it, this is the result I get, and then I print the shape in order to get to know what is the samples features after after the data integration step. So here is the finalized data. I export again the data and store in my Google Drive. So next, I would like to explain for the SNF data integration. All the pre-processing steps are similar, just the data integration method will be different. So same, I import all the data set that store previously during the pre-processing step. And then I set the patient ID as the data index. After that, I import the necessary files that required for the similarity network fusion data integration. And then I import SNF PY file for the SNF. And then from that file, I import data sets. So methyl is set as a dframe 1. miRNA is set as dframe 2. And then and then SCNB is set as dframe 3. After that, I calculate the similarity matrices using the pairwise distance. So this is the code that I use for the pairwise distance. And then I add back the patient ID to the column. So here is the affinities that I use for SNF for the data integration. And then I print for each of it for methylation, miRNA, SCNB. And here is the fused integrated data set. After that, I print the fused data set. And then here is the finalized SNF data set. So here is the code that we can use to for the similarity network fusion integration. And then I store back the data set in the Google Drive. So after the data integration method, we can proceed to develop the model. So we have few steps before we can proceed with the one-dimensional 1D CNN, one-dimensional convolutional neural network. So first of all, I import Keras and then PIP install Keras. So this is the supports nested progress bars. After that, I import all the necessary files that required for the development of 1D CNN for classification of breast cancer. And then this one is the TensorFlow version control. So it is, if it shows true means that one is eager execution is enabled. And then here is the Seaborn style description. And then same, I mount the drive and set the data path for the data set. And then I check for the machine run type. After that, I import the data set here, the data set after the data integration method. And then I display the integrated single omics variation data set. After that, I carry out RFE method. So the SPM RFE, the feature selection. So before we proceed to the feature selection, I did the data aggregation. So this features retrieve all rows and leave the last rows, and the target one will retrieve all the rows, retrieves only the last column. So it display the feature size and also the target size. This one is for the concatenated data integration. So after that, I did data normalization after data integration. So I no need to carry out for each of the data sets separately. So here is the data normalization. So I use min-max scaler. So data normalization is usually a method, a step, which will set the data set in the range of 0 and 1. So here is the scaled feature, and then I display the features. So here is the SPM model because the feature selection that I applied for this thesis is SPM RFE. So here is the SPM RFA. I set the parameter and create SPM model using a linear kernel. After that, I print all the coefficient of features. So after that, I did RFE implementation. So I find the minimum weight among features and eliminate the feature with the smallest weight. So the range was set to 20,946. So the remaining data set after RFE implementation will be 10,000. So here, this one is a loop which iterates until the final feature. So after RFE, so I print the features. As I said, there is only 10,000 left. So this one is the normalized features. And then I applied smooth. Smooth is the synthetic minority oversampling technique. So this is the process that carry out to balance the imbalance data set. So as you can see, so I assuming the data set as a column name class for the target labels and count the occurrence of each class. So I define the specific colors for each of the class and plotting the class imbalance with the specific color. So 0, which is a luminant, represent in pink, and a luminant B in represent in blue. And then I did for the class balancing. First of all, I did a data splitting. So data splitting was 75 35. So the training will be 75, testing will be 35. So I print the data shape. After that, smooth model fitting, and then I visualize the balanced data here. So this is the balanced data set. And then we can proceed to implement our 1D CNN, which is one-dimensional convolutional neural net. So before that, I set random seeds for reproducibility and then setting the random seed. So then the reason for setting the random seed is during the execution of 1D CNN, the accuracy will be remain the same. It will not change whenever every time I execute the process. So assuming features and target are defined and standardize the features. After that, split the data into training and validation steps. After that, apply smooth to balance the training data. And then I reshape features to 1D CNN input form. So here is the hyperparameter setting for 1D CNN. The sequence length was 10,000. Learning rate is 0.001. Filters is 32. Kernel size is 3. Dense units is 64, dropout rate is 0.5. And then here is the code that define the 1D CNN model and custom callback for adjusting the learning rate. And then here is the model compilation. I build and compile the model and display the model summary. So here is the model summary. After that, training data formatting, smooth and 1D CNN fitting. So now equal formatting with X test and equal formatting with Y test. After that, I print the shape of X and Y. Here, I assuming df is the data set and convert data frame to numpy array. After that, calculate the number of samples and features based on the size of the original array. And then I calculate the number of features per sample. Reshape the array to the desired shape. And assuming I have following all the code above and store the features and labels here as X and Y. After that, I create a random forest classifier and perform cross validation with 5 folds. And then I print the cross validation. So here is the cross validation score and also the F1 score. And then I fit the 1D CNN model using the history equals to 1D CNN model. So it print the 100 approaches here. And then I print out the pre-trained 1D CNN model loss. And then here is the pre-trained 1D CNN model accuracy. So after that, I print the validation loss and validation accuracy. Validation loss for the concatenated data integration was 1.1288 and validation accuracy was 66.67. And then I build the confusion matrix. So here is the code that I use for 1D CNN. it contain of dropout layer, convolutional layer, add layers, dense layers, everything. And then I print the 50 approaches here. After that, I print out the confusion, the rough picture of confusion matrix with class 0 and 1. And then here is the code that I use to advance the confusion matrix by replacing class 0 with luminant A and class 1 with luminant B. And then here you can see we have numbers on the confusion matrix with accuracy of 0.8182 and misclass of 0.181. And then here, if you see there is no value at the side, especially for the true positive. So we will have we will do not have value for recall, F1 score, everything. So we have to do fine tuning in order to have a values on sensitivity, recall, precision, F1 score. So this one is the 1D CNN model loss and 1D CNN model accuracy. And then and I generate training history table here and extract the training history, create table with matrices and loss values and print the table using the tabular function. And then I create a confusion matrix formula again, and in order to adjust the value so that there will be value at the true positive. So this is the confusion matrix after we pre-train, and the accuracy was 0.7879, precision 0.33, recall 0.1667, F1 score, sensitivity, and specificity. So here is the 1D CNN model loss, and it's quite overfitted. And here is the accuracy graph for 1D CNN. It also overfitted. And here is the comparison of model loss and accuracy. Okay, let's move to SNF integrated. So all the steps that are repeated at the concatenated data integration will be repeated using SNF. So but the only difference was there are few differences, which is at the RFE implementation, because previously we used 20,000 something, but here we just use 17. So it will eliminate 17 features only, and then there will be remaining 150 actions. And then we do the class imbalance and we balance the data. So this is the pre-trained 1D CNN model loss and 1D CNN model accuracy. So we have validation loss as 0.622 and validation accuracy as 68.57. And then same, we repeated all the steps here. As you see, there is no value at confusion matrix, and we modify there is value at confusion matrix. We replace class 0 as luminant A and class 1 as luminant B, and the accuracy was 0.8571 with misclass of 0.1429. And then we did the same thing. We create the random forest classifier and train the model, and we visualize. So there is no value at sensitivity, precision, recall, F1 score, same as the previous one. So here is the 1D CNN model loss, 1D CNN model accuracy. And then we apply the fine tuning in order to have a value at true positive. So after we adjust the code in order to have TP, so this is the confusion matrix with the predicted label accuracy of 0.8286 and misclass of 0.1714. So as you can see here, we have values for all of the accuracy, precision, recall, F1 score, sensitivity, and specificity. So this is the model loss and model accuracy, and it's overfitted. And then here is the comparison for model loss and also model accuracy. So that's all from me. Thank you for listening to my video.